Good afternoon, everybody. So today, me and Isabel, we're going to talk about a topic that you may have heard maybe many times, or maybe not, because those metrics of Sigmafine, those results of Sigmafine, are something that not all Sigmafine users know. So we will see now which are the metrics that Sigmafine provides you to understand which is the quality of your data and to monitor that quality. So these are the topics where we're talking about. A brief introduction. Then Isabel will show you more in detail those metrics, those Sigmafine results. Then we will see some examples, some business cases, some applications, and finally some recommendations. So let's start from the very basic definition of Sigmafine. This is the definition that you may know, everybody of us know by heart, maybe. So Sigmafine is a data reconciliation platform that provides you consistent data, and so permits to improve the consistency and the quality of your data. But more in detail, so we heard about that data conditioning. So Sigmafine provides you data conditioned for the desired state of use. But while doing this, while conditioning data, Sigmafine what also does is help you in providing also those metrics, those results, helps you in identifying the quality of your data, because the output, you know, that depends on your inputs, and Sigmafine helps you to understand which is the quality of your initial data and to monitor it. And why this is possible? This is possible because Sigmafine is model-driven. We saw it already. So this means that you will have a model that represents the process that you want to balance. With all your measurements, all your instruments, and all your assets that you want to represent. And so your measurements here are all validated one against the other. So that's why it's possible to validate your data and improve the quality of your data, because they are all set up on a model base. So all of us know that in order to get conditioned data and to have conditioned data as we want, I mean good conditioned data, we have to do some steps. So we have first to build a model, and maybe we'll have to validate it, make some first runs, and so start checking what's going on your balance and on your model. So maybe everybody of us remembers which was the first impression when you had the first run of Sigmafine the first time. Maybe it was this, okay? Why? Because maybe most of us, we all have maybe a big model with many measurements, many information. So the very first time you may have dealt with the quality of your data and the quality of your model. So maybe you may have had negative reconciled values, big variances, and so maybe somebody can say, Sigmafine is not giving me the results I'm expecting. Well, no, Sigmafine is maybe just simply trying to give you some warnings and some desperate warnings about maybe how your data is, and if maybe your model is not good, okay? So, in fact, there's always a reason why you are getting some results and you're getting some maybe bad initial reconciled value. So these are the main sources of imbalances and of error in that you may have in your model and in your runs. So first of all is model inconsistency. So as we said, Sigmafine is model-driven. So the model that represents the process that you want to balance is the basic of everything, the base. So if you have a bad model, so a model that does not reflect exactly your process, you may have bad reconciliation. So you can have unbalanced data. So the first thing is to set and validate your model. So that's what we normally do during the project. So we first build the model, but then we have an important phase that is the model validation, because as far as you don't have a model validated, you cannot go on, because it's like having a systematic error in your runs. Then, okay, you may have unsolvabilities. This means, and this is another result of Sigmafine. Sigmafine can give you an idea of which solvability and which unsolvabilities you have in your model, and how good is the redundancy in your model. So if you have some unsolvability in your runs, you have to take an action, and you have to avoid those unsolvability by or reducing the detail of your modeling, or adding some additional measurements if you have. Or you can have another source of imbalance, can be missing transfers. Many of your applications have also transfers included in the balance. This means that they may come from an external system, and so they may be logged by external operators. So they can always miss a transfer, or they may log a transfer in the wrong way. And so Sigmafine can also tell you how good are your operators to log the transfers in the right way. And in case it's a transfer is logged back in a bad way, you can see it in Sigmafine. So, or for sure you can have bad measurements or missing measurements, and again, this is a source of imbalance. So Sigmafine provides you all a set of metrics. We can say it's hidden results of Sigmafine, because most of us always concentrate on the reconciled value and to check what's going on with the reconciled value, but Sigmafine also provides you other results, and all this set of metrics that permits to understand the quality of your results and take action to improve the inputs in order to improve your outputs. And these are the metrics, so solvability and redundancy. Then we have the test factors for the meters, so test 1 and 2. The test factors for the balance points, there is the 3 and 4. And the model quality indexes that are 4 or 5. And each of them tells give you an indication on the overall balance, overall result in your model. So now Isabel will show you more in detail those metrics and those factors.
So in this section, we are going to explain with more details the main calculations performed when you done a run step. As Katia mentioned before, we have the model solvability and the statistical indicators that they are information hidden for the user, because not all of them now know about this topic. So let's start. Sigmafine first examines the measurement information available in the model, and then determines which other ones can be calculated from this data. This is called solvability. This solvability is calculated for a flow and transfers, and in this first step, Sigmafine assign this naming. So with the solvability, the solvability give you an idea if, for example, for a measurement that is not present on a flow, this measurement can be calculated or not. Of course, this measurement can be calculated only if enough of the surrounding flows are measured. For elements that are marked as auto-service, the solvability will not calculate it. So the naming convention applied for the flows is R when the flow is redundant, so the flow is measured and also solvable, and R when the flow is measured but is not redundant, S when the flow is not measured but is still solvable, and S when the flow is not solvable. For example, in these two schema, we can see how the redundancy reduces only because we have one measurement less. In the first schema, of course, anyway, Sigmafine can calculate the measurement of the flow from the other two flows because are measured. But in the second schema, we can see how the redundancy change only because we have one measurement more. So the flow becomes redundant, and as a result, the other two flows becomes also redundant. So more values can be cross-checked, increasing accuracy and obtaining better results. The statistical indicators are done in each measurement and in all balance points. And this test can give you an idea of the match of the reconciled and measured values. Specifically, the test 1 evaluates the fit of the reconciled value for a measurement relative its tolerance. This test is calculated for a measurement for ammeters. So if the results of the test 1 is within the range of +1 and -1 and +1, means that the correction is within the tolerance. So the reconciled results are good values. But if we have the results of the test 1 outside this range, means that the correction is greater than the tolerance. So in this case, these values are abnormal and needed to be checked. The results of the test 1 can be used to assess meter maintenance. So we have the results of the test 1, and we can plot we can see the behavior of the meter, and we can plot the reconciled mass and measured mass versus time. And in this case, we can do a tracking of the performance of the meter. And in this case, we can see for these two trends, process book trends, we are reading the reconciled mass, measured mass, and versus time. And we have here about 3 months of daily cases reconciliation. So comparing both reconciled mass and measured mass, we can also find the possible problems. For example, for the first meter, we have a bias error. That means that the correction or the difference between reconciled mass and measured mass is always almost the same. It's a systematic error. Maybe you are here in the situation, your instrument is not calibrated. In the second one, in the second trend, we have a drift error. That means that the correction between the reconciled mass and measured mass is higher during the time, and it can be even worse. That means maybe you are here in the situation that your instrument is broken. Another statistical test is the test 3 that represents the ratio of the balance error by the balance variance, or the uncertainty around a balance point. This test 3 is calculated for the balance point and is a measure of the overall quality of the data, and of course is used to identify the significant quantity imbalance. Here also, if we have results of the test 3 as an absolute value greater than 1, means that imbalance condition is greater than we expected. Another results from Sigmafine, very important, is the reconciled residual attribute that give you an idea of the imbalance of reconciled masses around a balance point. So when you are analyzing the results of the test 1 and test 3, you must examine any measurement and identify which of them constantly give you values in absolute value greater or equal than 1. For example, in the first case, in the case A, we have 1 meter with the results of the test 1 in absolute value greater or equal than 1, and the balance point near to this meter, adjacent to this point, should be also the results of the test 3 for this balance point should be also in absolute value greater or equal than 1. In this case, Sigmafine determines that probably the cause of error is the test 1. But in the case B, always with the meter, with the test 1, with the value in absolute value greater or equal than 1, but one of the balance point has the results of the test 3 in absolute value less or equal than 1, means in this case that the node B does not produce a gross balance error, but probably the cause of error is the node A. The tool that helps to the end user to identify the data issue and analyze the test factors is the Sigmafine Diagnostic add-in. We can configure and assign colors in order to highlight our problems in our model. For example, we have here a window with the name of the meters, and we can identify with the colors which elements have the problems. And in this way, we can see these values in a window and also in our model. We can also navigate and locate in easy way between the elements. We can also use the balance point window in order to check of inputs and outputs in terms of measure and reconcile values, and as well identify the initial imbalance and the reconcile imbalance. Sigmafine also includes the model quality indexes called DX. These DX are calculated with measure and reconciled values, and these DX evaluate and it's very useful to evaluate and monitor the overall quality of the model. The most important DX are DX0, DX1, DX2, where DX0 is a KPI that quantify the amount of flowing material is going that is not subject to the redundancy. The target value is below 30%, but if the target value is higher than 50%, that means that it may not possible to calculate the errors with accuracy. So maybe probably you need to add more measurements. Let's say physical measurements or measurements derive the other calculations. The DX1 is another KPI that summarizes the overall quality of the model by examining the imbalance in all balance points as ratio of the redundant measurements. The target value is below 10%, and this DX is very strongly correlated with the data quality of our facility. The DX2 indicates the amount of adjustment that the Sigmafine solver had to do in order to satisfy all balance. So Katia can introduce some examples.
Thanks. Okay, so let's see some business cases. So some application of those KPIs, how they are used by our customers in their daily work and daily operations. So this case is a case of Chevron. It's a refinery in the US, in El Segundo. They have about 30, 35 process units. And since when they started to use Sigmafine in 2009, they started to track the DX indicator, the DX1 indicator, that is the one of the imbalance. So the DX, it's quite powerful because with one number per case, you know which is the overall imbalance of your model, so of all your measurements, or all your balance points. So as you see, as you see, they started in the first runs. They started with the quite high value of the DX, DX1, and with the time, this is actually a 2 years plot. With the time, they could, I mean, improve the quality of their data, and so they could improve the value of this DX1. So, as you see, as you also saw from Orpik presentation, so it's a journey. So you start from something that for sure you need still to validate, that indicates how good are your data, and taking action on data, so improving the way in which you log your transfers, putting more measurements, calibrating your meters, you can arrive to improve the final value of this DX. So they could even reach, finally, a much smaller value, of which is of the suggested target. So the suggested target is below 10%. Now they are at 2.5%. So start from panic and you go to good data. Then this is, okay, this is just to check if you remember about what Bernard said already. So we already showed this before. It's the case that Philips 666 presented during the Houston conference summit. It's just to summarize. So this case is quite particular because they use DX for a compliance to a law, to an accounting standard, okay? So when the accounters, at the end of the month, arrive there, the auditors arrive there to check their accounting reports, they show them the 3 indicators, the X1, 2, and 3, that they track daily in this report. And so if there is if a value of one of these for even one day is higher than the threshold, they have to justify it and they have to approve it. Okay. Finally, we have another case of Suncor. I think it's Canadian. Yes, it's a Canadian refinery. They have many. They run Sigmafine balances daily, and they have many type of reportings. One of these is done by the Tableau, and in Tableau they keep track of the imbalance of each unit for each day during the time. So as you see, for example, the first plot is the plot of the imbalance of a unit through a month, and so the red values are the values that are higher than the threshold. They keep track also of the T3 value, that it's similar, let's say, to the keeping track to the imbalance of the unit. And they keep track also of the T1 indicator, test 1 indicator, for some specific meters. And so here you see, for example, a meter that has some troubles, so they have or red values. So in this case, they had to take some action to let's say, improve the value of this meter. Okay, so let's finish with some recommendations and conclusions. So we saw that the model, the Sigmafine is model-driven. So first of all, when you build your model, the recommendation that you have to follow is that you build it in a good way. Okay, so it really reflects the process that you want to balance. And so in order to be sure that the model has done in a good way, for sure in the first runs you have to validate it, you have to make sure that all the measurements you need are there, you have to make sure that you have no unsolvabilities, etc. You may need to run, for example, the gross error analysis, at the beginning that can help you to understand if there are some unconnected meters or flows. And you, with the time, with the first runs, you may also need to tune the tolerances of your meters. In the daily operation, we recommend, again, to use the statistical factors to track the behavior and the, of your meters and of your balance. So use the DX indicator, use the T3 indicator also to track the performance of your meters. And in the long term, for sure, you always have to remember to keep up to date your model. So if your process changes and you add a unit or something happens new in your process, for sure you have to update your model in order that it reflects exactly your process. Also in the long term, you can track the performance of your meters and see what we saw before. Maybe if any meter or any unit is going too much farther in the imbalance and in the reconciliation.